we are about to discuss on parallel resonant circuit. So what is parallel resonant circuit? For a fixed amount of current, voltage goes on increasing, and when the when the impedance of the circuit increases, the current falls gradually. So in a parallel resonant circuit, the impedance in the inductor and the capacitance will be kept parallel to each other with their own impedance or own resistance. In AC circuit, we call the resistance as impedance, and in DC we will call it as resistance. So in a parallel resonant circuit, to find the current flowing through the inductor and the capacitance, we need to know about the admittance of the current. So we know that admittance Y of the circuit is Y is equal to Y1 plus Y2 because two branches are present, so Y1 plus Y2. What is admittance? Admittance is inversely proportional to inductance. So impedance. So impedance is the resistance offered by the circuit, whereas admittance is the current flowing through the circuit. So they are inversely proportional. So we can write Y1 plus Y2 as 1 by Z1 plus 1 by Z2. So what is Z1? So Z1 is, we consider Z1 as impedance produced by the inductor, and Z2 as impedance produced by the capacitor. So we write it as 1 by R1 plus XL. So we consider it as all, we will denote inductor as JXL and the capacitance as minus JXC to denote they are parallel. So by taking their respective conjugates, we get 1 by R1 plus JXL into R1 minus JXL by R1 minus JXL. So while taking conjugate, we can write it as R1 minus JXL by R1 square plus according to A plus B into A minus B is equal to A square plus B square. So R1 square plus XL square. Plus in the same way we do it for capacitance. So R2 plus JXC by R2 square plus XC square. Now we are writing those parameters separately. So R1 by R1 square plus XL square minus JXL by R1 square plus XL square plus R2 by R2 square plus XC square plus JXC by R2 square plus XC square. So segregating those terms with real and imaginary parts, we get R1 by R1 square plus XL square plus R2 by R2 square plus XC square plus J into XC by R2 square plus XC square minus XL by R1 square plus XL square. So we know that in admittance, we see only the current flowing through the circuit. So we consider this imaginary term as 0. So XC by R2 square plus XC square minus XL by R1 square plus XL square is equal to 0. So equating both the equations we get, and we are doing cross multiplication over here. So XC into R1 square plus XL square is equal to XL into R2 square plus XC square. So we know that the reactance offered by the capacitance is 1 by omega C, whereas the reactance offered by the inductor is omega L. So XC can be represented as 1 by omega C into R1 square plus XL square is equal to omega L into R2 square plus XC square. So R1 square, we are taking this omega C over that side. So it becomes R1 square plus omega square L square is equal to omega square LC into R2 square plus this XC is represented as 1 by omega C. So by squaring it, omega square C square. So R1 square plus omega square L square is equal to, we are multiplying it inside, we get omega square R2 square LC plus L by C. So we are taking omega terms on one side and other terms, so constant terms on other side. So we get omega square L square minus omega square R2 square LC is equal to L by C minus R1 square. So by contracting it, we get omega square into L square minus R2 square LC is equal to L by C minus R1 square. To make the equation so simpler, we do multiply and divide by LC on both this on left hand side. So omega square LC into L by C minus R2 square is equal to L by C minus R1 square. Because we can see the similarity between these both sides, L by C minus R2 square and L by C minus R1 square. So this can be convenient for us to proceed still more steps. So omega square LC is equal to L by C minus R1 square by L by C minus R2 square using regular mathematical notations. So find the value of omega. We write omega is equal to 1 by root of LC into root of L by C minus R1 square by L by C minus R2 square. We know that admittance is always positive and the omega value must be positive. Since the omega value must be positive, the circuit becomes totally resistive, and hence L by C must be always greater than R1 and R2 given in this circuit, this R1 and R2. So the formula gets reversed. So omega is equal to 1 by root of LC. This R1 square and the LC gets interchanged because we need always L by C must be greater than R1 square and R2 square. It should not be less than. If it is less, then we will get as imaginary term and the total circuit becomes collapsed. So we know that omega is equal to 2 pi by t. So 1 by t can be written as nu. So 2 pi nu is frequency, is equal to 1 by root of LC into R1 square minus L by C by R2 square minus L by C the whole root. So we need the frequency. So frequency can be written as 1 by 2 pi root of LC into root of R1 square minus L by C by R2 square minus L by C. So this is the formula for parallel resonance circuit. We obtain parallel resonance circuit formula by using these steps. So what are the characteristics or parameters of parallel resonance circuit is when the impedance at resonance increases. So during resonance, the impedance of the circuit gets increases, and at resonance the current decreases. Since the resistance increases, that is impedance increases, current gets decreases always. So we know it according to Ohm's law. So power factor at resonance is unity. So power factor is cos pi. So the phase shift will be in phase. So the power factor at resonance is unity. Circuit behaves like purely resistive circuit. Since the circuit is mainly based on inductance and capacitance, so the circuit behaves purely resistive. The condition for resonance at all frequencies, this R is equal to root of L by C. This is the condition we proved now. Thank you.